So let's start the problem on these thermal stresses. Okay, so there is a composite structure like this. We have a steel and aluminum structure. Okay, so the bars are stress free at 40 degrees centigrade initially, and what will be the stresses in the two bars when the temperature drops to 20 degrees. Okay, and there are two conditions. The first one is supports are unyielding, that means there is no gap. Okay, both are fixed like that, and when the supports are not fixed not fixed, but there is a yielding of 0.1 mm. Okay, so in these two cases we need to find out this. Okay, this is a little bit difficult problem. It's a little bit difficult in the sense, this is a mix of all the cases. So if you understand this, then no need to do other problems. Okay, so here the temperature is decreasing. So when the temperature is decreasing, what is happening here? Aluminum is having the more alpha than the steel. Okay, then aluminum try to compress more. It try to compress more. Then it is compressing only less, and when it is try to compress, it is try to pull the steel more. Okay, then what is happening? It is going in this direction, and because of this, because of this, what is happening? This is trying to pull in that direction. Okay, so what is happening here? There is a compressive stress in the aluminum, okay, and tensile stress in the steel. It is going in this direction, okay, and steel is going in this direction, trying to in this direction, but this amount is more. Then it is trying to pull this back to this side because of this junction, okay, attached. So here what is happening? In the aluminum, there is a compressive stress, and in the steel there is a tensile stress. Okay, and let's say this compressive stress or the force as the Fc, or we will put the symbol A, and here Fs. Okay, actually it's not small f, we will keep capital F. Sometimes we use small f for the stresses also, okay, to avoid the ambiguity. And what is the dt here? dt equal to 20 minus 40, that equal to minus 20. Why? Because final temperature minus initial temperature, degree centigrade. Okay, so we will take the first case. Okay, so in the first case I will start from here because there is a space constraint. So in the first case, supports are unyielding, or there is no gap here. Okay, there is no gap. When there is no gap, then these two rods are not allowed to contract freely. Okay, then these are trying to restrict their free contraction. When they are trying to restrict, then stresses are produced in that. And what are the stresses produced in this? There are two types of stresses. One is because of the thermal stress, another one is the forces, because of the forces. Okay, then first we will calculate the thermal stress, thermal elongation due to thermal change. So delta T S, okay, delta Ts equal to L alpha S, Ls alpha S delta T. Okay, Ls length of the steel rod is 500 mm into alpha value of steel is 12 into 10 power minus 6 into delta T 20. Okay, we neglect about, we don't take negative value here, then it will, how much value we will get? It is 0.12 mm. Okay, and then delta T aluminum. For aluminum I will put A. This is a LA alpha A delta T. Okay, LA is 250 into 24 into 10 power minus 6 into delta T, that is 20 here. Then I will get how much? Again here also I am getting 0.12 mm. Why? Because here this is in mm, so that's why we are getting mm here. Okay, so what is the total elongation? Total elongation due to total thermal elongation equal to sum of these two. So that is a delta T A plus delta T S. Then this is 2 into 0.12, that is 0.24 mm. Okay, this is the due to thermal extension. Now we know FA equal to Fs, and the elongation due to the forces equal to are, we know the formula from the theory. What is that? Delta T A plus delta T S equal to delta T A plus delta T A equal to, actually this is not T, otherwise I can write it as something like this. Okay, delta T. Okay, total elongation due to the thermal stress, temperature decrease in the temperature. Okay, here if you observe, why is this plus? Because one is compressive, one is tensile, so we are adding both. Okay, and that equal to delta F A plus delta F S. Okay, and what is this values here? This is because of the force. Okay, then this is a FL divided by EA plus FL divided by ES. Why F? Because here FA equal to Fs equal to, let's assume F. Okay, so we need to find out F equal to delta T. Delta T is 0.24. Okay, 0.24 divided by L. See here, this is a LA and this is a LS, because L is not same. Otherwise I will substitute there itself, so that it will be easy for us to calculate. So here this is a LA for the A, this is a 250 divided by area is 240 into, for the aluminum it is a 0.7 into 10 power 5. I am keeping everything in the mm. This is a 160, this is a 500 divided by AS is a 160 into ES is a 2 into 10 power 5. Okay, that equal to 0.24 mm. Okay, by simplifying this, then we will get F equal to 7867.317 Newton. Okay, so by knowing this we can calculate the stresses in both. So sigma aluminum equal to F divided by A aluminum. Then this is a 7867.317 divided by area of aluminum section is 240. Then it will get, this is a Newton per mm square, then you will get the value 32.78 Newton per mm square. Okay, in the same way sigma of steel equal to F by AS, then you will get 7867.317 divided by, what is the area? 160. Then its value is 49.17 Newton per meter square. So Newton per mm square. Okay, this is the first condition. Here, let me let me quickly go through what we have done here. So whatever the formula we have derived in the theory, we are using the same thing. Okay, what is that formula? This is the formula. But here you might be wondering why we are adding these two. Okay, this is the only point where it may confuse you people. Okay, why you are adding? Why? Because when you derive, this is a minus, and in that case we derive this formula for the composite bars which are attached to one another like this. Okay, and the compression or expansion in this case is in the same direction. These are in the same direction, so that the total elongation due to the temperature, is subtracting from each other. Okay, but whereas in this case, these two are in the opposite direction. See, when temperature is decreased, it is trying to compress in this way, steel one, and the aluminum is trying to compress in this way. These both are in the opposite direction. So if I want to find out the delta T, means total elongation because of the temperature decrease, then we are adding, this is adding and this is adding. Okay, these are in the different direction. Instead of different direction, if both are going in the same direction, then we would have subtracted. Okay, so you remember this logic here, don't get confused, and the remaining thing whatever we have done here is as usual, whatever we have derived in the previous lecture. Okay, now we will see the second point. What is that? Here in the second point, see, in the second point there is a yield gap of 0.1. then we need to find out the stresses. So what is the answer? Tell me. Answer is 0. Why? Because here, see, when there is a yield gap and here temperature is decreasing, when the temperature is decreasing, and here in this case, let's say there is a gap between the fixed support. Okay, this is the gap between the fixed support. See, when the temperature is increasing, when the temperature increases, then only it will go and touch this, and it will try to restrict this body, and it will produce the stress. But when the temperature is decreasing, it will move back in this direction, and it won't touch the fixed body, and that means there is no restriction at all. So in that case, the temperature is, the stresses are 0. Okay, the stresses are 0. But anyway, let's take, what if the temperature is increased instead of decreased? Let's say the temperature delta T is a positive 20 degrees. Okay, it is for the positive 20 degrees. Then in that case, okay, the formula is like this. See here, the delta T is a total elongation of the two materials because of the temperature rise. Okay, but there is a gap. What is that? A yield. Okay, by subtracting this, after that only there will be production of stresses in the bodies. Okay, then we need to equate this into delta F A plus delta F S. Okay, in the previous case this is missing, and here in this case we are substituting this. Okay, and again this can be written as F into, okay, L J by AA EA plus LS by AS ES equal to, this is a 0.24 minus 0.1. okay, if I substitute the values F into LA is, okay, LA is how much? 250 divided by area is 240 into EA is 0.7 into 10 power 5, okay, plus LS is 500 divided by 160 into 2 into 10 power 5, okay, equal to how much? This is how much? 0.14. okay, by simplifying this we will get F equal to 4589.268 Newton, okay, and we need to find out the stress in the aluminum, that is F by A, okay, then it is 4589.268 divided by aluminum 240, then its value is 19.122 Newton per mm square, okay. In the same way, sigma of steel equal to F divided by AS, that equal to 4589.268 divided by 160, okay, then its value is 28.683 Newton per mm square, okay. So we need to find the temperature stresses like this, okay. If you can understand this problem, you can solve any problem, any difficult problem. And here in this problem we have a brass here, and then its length is 30 mm, and the copper part is here, its length is 40 mm. okay, and their material properties are given like this, and the room temperature is 30 degrees centigrade here. So the room temperature is at 30 degrees centigrade. At how much there is a increasing the temperature, so that that gap will be filled up between these two, okay. And what is the gap between these two? The gap is 0.1, okay, 0.1 mm. The gap is 0.1 mm between these two. So here, see, because of the temperature rise, so there is a expansion in the brass and as well as expansion in the copper, okay. The combined expansion due to the temperature rise should be equal to the length of, the gap, okay. Here, temperature elongation due to the temperature rise in the brass B plus elongation due to the temperature rise in the copper equal to the gap. What is the gap? That is 0.1 mm, okay. And for this, what is the formula? Okay, the elongation formula L alpha delta T, okay. Here L for the brass, L is 30 into alpha for the brass, how much? 10 into 10 power minus 6 into delta T, okay. Delta T we know, that is what we need to find out, how much increase in. Let's say the final temperature is T2 or the T minus 30, okay. This is what we need to find out, temperature T, plus for this L alpha T, okay. Here delta equal to L alpha delta T, okay. And here length of the copper, what is the length of the copper? That is a 40 into alpha of the copper, that is a 15 into 10 power minus 6 into temperature difference, that is T minus 30, that equal to 0.1, okay. By simplification, then you will get delta T equal to 111.11 degree centigrade, and final temperature delta T is nothing but delta t is nothing but t minus 30 equal to 111.11 degrees centigrade, then t equal to 30 plus 111.11, that equal to 141. okay, 141.11 degree centigrade. okay, the final temperature should be raised to 141.11 degree centigrade, so that both will expand and fill that gap. okay, like this, based on the logic or based on the question, we use the same formula again and again. What are this formula? This is the formula. And what is the logic here? When the elongation is restricted, then there is a chance, there is a production of stress produced in that case, and we need to find out stresses in such cases here. okay,
For engineering services general studies video lectures, visit www.iesgeneralstudies.com. For mechanical engineering video lectures and question and answer discussion, visit www.getnet.com.